I'll be presenting today on low-cost fiducial-based 6-axis force torque sensor. In this paper, we created a sensor which is up to 1,000 times cheaper than some of the more expensive commercial ones by relying on these fiducial tags, which I'll cover in more detail later. To take a step back, what we're looking at is considering the fact that we are all working in robotics because we think robots can help improve our everyday lives. However, they're really still kind of stuck in factories and roads even, but not in our homes. So when we think of domestic robots, we think of nowadays single task robots like dishwashers, laundry machines, robot vacuums, and we're really missing the more general purpose robots. And in order to bring robots into our homes, we really need a combination of locomotion and manipulation. So locomotion, we have great advances in the last 2 decades. ASMO 2000s, fairly conservative, Boston Dynamics 20 years later, these really dynamic backflip movements. On the other hand, manipulation has been kind of stuck in this bin picking scenario of picking and placing where we've gone really far, but we haven't moved on into the next step. And one thing I would like to note is that both of these tasks involve going this shift from avoiding obstacles to seeking contact. So the challenges in bringing a robot into the home include this usefulness to cost ratio becomes important. So you can consider that on one hand, a robot hand with the end effector arm might cost up to $30,000 and more. On the other hand, with a washing machine, a dryer, a dishwasher, and a robot vacuum combined, I can get one of those for less than $2,000 due to economies of scale. So clearly there's work to be done in making robots cheaper. And in particular, our focus is on contact. Now that we are manipulating things, we are dealing with contact forces and torques. So creating a novel 6-axis force torque sensor for the XYZ forces and the moments around those axes. So we focus on this fiducial-based design where you have this tag, which is a certain pattern, printed out, affix it to an object, and then with a webcam and computer vision standard algorithms, we can back out the pose of the object. So our sensor design is based on this, where we have this floating platform up here, and underneath we have this camera, which is pointing up at these two tags, which are affixed at 45-degree angles. And the bottle cap is just for scale. It's a fairly small sensor. And so what happens is if we were applied a force to the top of the platform, then you can see in this video what happens, which is from the bird's eye view, you can see the sensor is moved and then the camera image moves accordingly. And with this pose estimation from the tags, we're able to get displacements. And this diagram is just reiterating that we have this at rest when it's displaced with a force, the tag moves sideways, and then when there's a moment, the tag rotates, and so forth for all the axes. So the reason why we're interested in working with these fiducial-based designs is looking at some of the existing sensors out there. We have really state-of-the-art sensors like the ATI sensors, which are great, but they're expensive, thousands of dollars, and kind of fragile. We also have more consumer-oriented sensors like the Space Mouse. However, these are really not meant to be modified. And we also have more research-grade sensors such as tactile and other elastomer-based sensors. They're inexpensive and they're robust, but fabrication it's kind of messy and uses specialized machines. And on the other hand, if you compare it to this fiducial-based design, you'll see that we have this benefit of being inexpensive. In fact, the most expensive cost in this case is just the camera, which is maybe $20. So in total, less than $50. It's easy to fabricate because it's literally just these 4 3D printed pieces. And then we have the springs with some glue and just put it together with the LED and the camera. So it's easy to integrate into designs and it's robust because we're using a webcam. And here's a case study and the fact that it's really easy to modify. So going to the supplemental website, which has some more materials and the supplementary video, and also note the design and code files, we can see the use case where I wanted to create a sensor which had bigger springs and also added in a coin cell holder for the LED. So here you can see some of the supplies used for making the sensor, pretty straightforward. You can definitely have them in your home without too many safety concerns. And then here, the design files are already online. So just take those, edit them, and then print out the files after they've been edited for the bigger springs. And then we can then apply the heat set inserts with a soldering iron, then cut and glue out the tags, paste them on, and then also glue in the springs. After that, just tap in the bolts so that we can bolt the camera to the rest of the sensor and just solder up the LEDs, and then we have a working sensor. So here, just kind of showing the finished sensor, which is made in just a few hours. So it's printed fast, so that's why there's some missing bolts and such. But here you can sort of see the degrees of freedom. It has all 6 degrees of freedom here, which is how we are able to measure the 6 degrees of freedom for our 6 axes of force and torque. And so because it's just a webcam, we can just plug straight into the computer and just run a Python script and immediately start getting data. Obviously, this data is not calibrated, so it's not in absolute values or anything, but it does work. And here you can see that you can even just connect the webcam to a browser and get data out. So in this case, I made just a little high five demo. The robot moves forward, and then it stops when it detects some force being applied. And so you can see from start to end, I was able to make this application with this modified and new sensor in about 9 hours. So going back to our presentation here, we have this fiducial-based design, but it's important that it also actually work. And so the next step we did was to validate it experimentally. And so in this case, we used an optoforce as the ground truth sensor. And so we got our forces and moments out of that, and we just did a linear fit. So we also took the displacements that we got out of the 6-axis force torque sensor and from our optoforce RUCO tags, and we did a linear correlation between the optoforce and the RUCO tag to get our 6x6 calibration matrix. And looking at the results, it does look like that there was a fairly linear relationship between the optoforce and the RUCO tag. So note that in this case, this is under multi-axial loading. And so I'm literally sort of manually toggling the sensor around. And so you can see here in black, this is if there were a perfect correlation linearly between the optoforce and the fiducial sensor. And in red are the measurements that are linearly interpolated from the RUCO tag. So the X and Y data look fairly good. And the Z data is a little more noisy. And you can see here a reconstructed signal example. And so there's the Z-axis, the force being a little noisy, it might be to be expected, as you might imagine. When you compress the sensor, the tag is moving in and out towards the camera, which is actually like relatively little pixel change compared to if the entire tag were moving back and forth across the camera frame, like in the X and Y direction plane. So we can kind of expect that noisiness and have to work with it by adding, say, the dual tag setup. On the other hand, the Z moment is a little unexpected. It may just be due to the dual tags. They're not quite facing the camera, and there's some averaging issues going on. So to summarize, we have these tactile sensors useful for manipulation. The new idea is to use fiducials. Note that it needs a really bright LED with a diffuse cover, and using two tags at 45-degree angles to get a clean enough signal to be usable. So it works, but the Z-axis force and torque isn't so precise, and the bandwidth can be low. Optoforce outputs at 125 Hertz, webcam at 25 Hertz. It's just a standard webcam. And so included, and the sensor is inexpensive, it's robust, it's easy to make, use, and modify, and it's open source, but in its current state, it's not a precision instrument and it's low bandwidth. So to look at that further, we can see modify it to suit our desires. So for instance, with the camera, if we want it to have faster bandwidth, then we use a faster camera. However, that might be more expensive. We could also use a zoom lens, increase the sensitivity, but decrease the force range because the tags will go out of frame. The same for the fiducial tag part. We could use more tags, get more data to get a better post estimate, but that would decrease the force range because all the tags need the same frame. And to address the Z-axis noise, we did consider using mirrors. Please see the paper for more details. And for the springs, we can also increase the sensitivity by using softer springs, but decreases the force range. And for making the design smaller, we could use a smaller camera, however, that would be less user-friendly. So just the possible design space. So in summary, we have used this fiducial design to enable a new class of 6-axis force torque sensors, which are not limited to being used in robotics applications. And so this, if you would like to know more, please see our paper, Low-Cost Fiducial-Based 6-Axis Force Torque Sensor, for more details, and visit us online for the code and design files at the URL there, and see y'all online.